All right, so last time I left you with this website to kind of explore on your own. I do want to illustrate one of the ideas that I wanted you to get from that website. So so you go to this page, you go to statistical applets and normal density curves. So right now it's kind of showing the tail area. I think if we update, I don't know. Oh no, I couldn't do this. I was having problems with oops. I was having problems with Chrome, but I was having better success with Microsoft Explorer with the applet. So here's the applet, and if you take off the two tail, you can kind of move the two buttons independently. So from 0 to 1 standard deviation, this is the value that I illustrated on the calculator. Okay, but you can kind of move it anywhere you want. If I go two tail, then it'll kind of give me a symmetric. So what percent are within 1 standard deviation below and 1 standard deviation above the mean? Well, that's about 68% of the data points if you have a normal distribution. So what happens if you extend it to 2 standard deviations below and 2 standard deviations above? Well, that's about 95%. Next question might be, well, what about 3 standard deviations above and below? Well, that's 99.7%. 4 standard deviations, I guess we could go. We're getting like 99.99, and I don't know how accurate this goes to. Now, this distribution does go on forever, so we could find that what's the probability that like that. I don't know if you guys remember the z-scores for Babe Ruth and Barry Bonds. I think Barry Bonds is like 2.79 or something, somewhere right around there. Now, unfortunately, I can't have this thing go all the way to infinity. So the probability that you're between these two would be 0.003%. So as you get way over here, like I said, I wish I could make this thing go all the way up to infinity on the upper bound. There's the probability of these things happening, assuming a normal distribution, are really, really small. But you can calculate the area between any two curves or any two cutoffs, and between these two, it's about 7%. So we use this to model data in the real world. Okay, so this is called sometimes the empirical rule, sometimes it's called the 68, 95, 99.7 rule. If you have a normal distribution, that's the key point here. You have to have a normal distribution. Then 68% of the data points are within 1 standard deviation of the mean, 95 are within 2 standard deviations of the mean, and 99.7 within 3. So we just kind of remember these 3 values because they're the most common. A density curve is uniquely determined by the mean and standard deviation. A shortcut notation for the normal curve is normally distributed with a mean of mu and a standard deviation of sigma. So you kind of just put those values in there. Properties of a normal curve. It is unimodal and bell-shaped, not approximately symmetric. This thing is perfectly symmetric. It is completely determined by these parameters. The mean determines the location of the curve along the x-axis, and the standard deviation determines the spread of the curve. The mean, median, and mode are all located at the line of symmetry because it's perfectly symmetric. And 1 standard deviation above and below the mean takes place at a point of inflection. That's one thing that I guess I could talk about. If in your other classes you guys have studied point of inflection, where this thing turns from curving down to curving up, that is the point of inflection, and it takes place at one value, at a standard deviation of 1. On this curve here, if I go to menu, analyze graph, inflection point, and go boom, boom, you can see the point of inflection takes place at exactly 1 standard deviation below and 1 standard deviation above the mean. Okay. Excuse me. So let's sketch a normal distribution with a mean of 40 and a standard deviation of 3. So get used to just drawing a nice symmetric bell-shaped curve. That doesn't look so good when I first, you're not going to get it perfect. It's fine. Just, it's a sketch, but unimodal and symmetric. Then the mean is going to be right in the middle, so we'll call that 40. And then one standard deviation is going to be where this thing goes from curving up to down. So right there, call that 3 above the mean, so that would be 43, and then scale it. If that's 3, then the next tick mark would be 46, and 3 standard deviations above the mean would be at 49. One standard deviation below, about 37. One more tick mark below that would be 34. 3 standard deviations below would be at 31. So that's a sketch of the distribution, normal curve that has this mean and this standard deviation. Estimating the mean and standard deviation. Because if you have a normal, approximately normal, a symmetric mound-shaped curve, if you kind of fit a normal curve to this data set, kind of just draw it as, it's just an approximation, but if you kind of fit it like that, you should be able to kind of estimate the center, and if you go to the point of inflection, you can kind of get an estimate for the standard deviation as well. So I would say the mean is about 60, oh, not 69, I'm sorry. 60, what is this, 60, 60. So each of these tick marks is 2 units, so that'd be 70. Looks like the scores, so score 70. And the standard deviation would be about, well, one standard deviation looks like it's to this tick mark, so that's 60, 70 to 74. So about a standard deviation of 4. So it's a way to kind of estimate roughly the standard deviation. Your teacher reported that the scores in the last test had a mean of 70 and a standard deviation of 10. Sketch the distribution along with appropriate scales and labels. So let's draw our normal curve. Center would be at 70, one standard deviation below, turning from up to down. I'm going to say that's right about there. It's kind of where it straightens out. So I'll call that 80. 2 standard deviations, 90. 3 standard deviations, 100. Standard deviation below, 60, 50, and 40. Labels, I guess we should say score, test score. We could put a title up here if we wanted, but whatever. Find the approximate percentage of kids that scored between 60 and 80. So 60 and 80, that's going to be here to here. That's one standard deviation above and below. So if we remember our little rule of thumb here, that is about 68%. What percent scored between 70 and 90? Well, 70 and 90 would be 70 to 90. So that's 2 standard deviations. So if I went from 2 below to 2 above, that would be a total of 95%. However, I don't want the below, I just want the above. Well, because this distribution is symmetric, I guess we could just half that. Oh gosh, half of 95. 47.5. 95 divided by 2. I knew it was 97, 47, just teasing. About 47.5%. How about above 90? Well, we just said this was 0.475. Because this is symmetric, I know that this holds from here to infinity is going to hold exactly 50%. Well, if I want 90 or above, I could just take this 50% and subtract this 0.0. Or another way to look at it is, yeah, let's just do that. Another way to look at it is, let me start fresh here and show you to you another way here. Oh, geez. Oh, geez. Just wanted to erase some things here. So here's another, what I just said was right. It wasn't incorrect, but this is maybe a better way to look at it. As I said before, 2 standard deviations above and below, that gives you 95% total. That means there is 5% left over on these two tails. Well, if you divide that 5% into 2, that means there's 0.25 on each tail. So that means above 90, that's about 0.25, also known as 2.5%. Suppose 1,000 kids took the test. How many would you expect to score above 100? Okay, so now let's make the same argument for 100. For 100, that's actually 3 standard deviations above to 3 standard deviations below. That's 99.7% of the data points. That means for these two tails, it's got to be that last 3/10 has got to be split between them. So that means 0.0015 and 0.0015 on each tail. So if the probability is 0.0015 and you have 1,000 kids, I guess we just move that decimal over 1, 2, 3. So you would expect about 1.5 kids to have scored that well. So that's not, you might say, well, 1.5, well, sure, on average. Sometimes 1, sometimes 2, sometimes 5, sometimes 0, but on average, it'll be about 1.5 kids. So this is a measure of how unlikely it is in a normal distribution to be 3 standard deviations above the mean. It's not very rare. I mean, excuse me, it's extremely rare.